so there's that. Let me ask you this. We're going to get into section 3.7. A little review of section 3.6. Especially since we're going to have a quiz on it next time. 3.6 is where we learned about the natural log stuff and logarithms in general. I don't think I did. So if I have this, what's its derivative? Cool. Now real quick, how would I investigate? What about if I had this? Let's just say log base a of x. Let's make it very general. What's that guy's derivative? Oh, no shit. So how do I start to investigate it? Who can give me an idea of what to do? Can I rewrite this in a form that I know all the derivatives? Sort of like a overriding theme. Yeah, okay, a to the y equals x, so x equals a to the y. That's just the idea of logarithms, right? And to be honest, you could do implicit differentiation, but can't I do something to both sides to see exactly what y is? Something that I know the derivative of. Natural log, so natural log of x equals natural log of a to the y. How do I rewrite this? Y times natural log of a. So y is natural log of x over natural log of a, which some of you guys might realize we just kind of reproved the change of base formula. You guys remember the change of base formula? The shortcut to remember it is base on the bottom. Base on the bottom. I mean, it's lovely. It's lovely. Okay, so how do I do this guy's derivative? What is ln of a? What kind of thing is it? It's a constant. I love it. So it's like 2. Right? So what's the derivative of ln of x? 1 over x, and there's that constant just coming from the right. So what's the derivative of log base a of x? 1 over x times ln of a on the bottom. That's just the same thing as the derivative of a to the x. It's got that stupid little adjustment in case the base isn't e. If this was e, if the base was e, if this was ln of e would be 1. We recover that. So it shouldn't be that big of a surprise that this has an adjustment the same way that a to the x has an adjustment. Remind me, what's the derivative of a to the x? Yeah, a to the x ln of a. So that same ln of a adjustment shows up here also because the base wasn't e. It's beautiful. It's the same reason. Yes?
Why don't you do ln of a squared?
Oh, it's not quotient rule. This is 1 over ln a times ln x. What is 1 over ln a? What kind of thing is it? A number. It's a constant. So it's 1 over x times 1 over ln a. That's why you get this. If you did quotient rule, do it. You'll see that one of the ln a's cancels. Ln a prime is 0. Yeah, it's just over much. You don't need to do all that. All right. So the top or the bottom of a quotient is a constant. Good God, don't do quotient rule. Holy shit. Right? No. There's much easier ways to do it. Maybe. So on Thursday we'll have a quiz. 3.5, 3.6. 3.6 was all about the logarithmic stuff. 3.5 was that partial? Was that implicit? Yeah. 3.5 was implicit. Solving for dy dx. That stuff. Okay. Let's get into 3.7. This is getting into the sciences and how they use. Oh my God, you can't go very far in any science without calculus. In fact, I don't know if any of you guys have to take differential equations sometime in your future. Does that sound familiar? Once you learn diff and q, and you take any science, you're like, how did I do anything before I do differential equation? So what does a derivative tell you? Slope. And now tell me more physically, what does it tell you? Rate of change of something versus something, right? So like I said before, flow rate. Very often we know flow rates. We know how quickly something is changing, but I want to work back to see, well, what amount is there at a certain time? So I've got to anti-differentiate. So that's really what differential equations is all about. If I know how rates are related, I can work backwards to see how amounts are related. Right? Like an underivative. So later we'll give it a better name. But the very first thing we do with this is the most fundamental thing you do if you take a physics class. We should talk about something called kinematics, right, which is a study of motion. So if I give you a position function, have we done this kind of thing before? What letter, do you guys remember what letter we use? S, just because. So if I give you a position function, how do you think you get the velocity function from that? That's crazy. So if I do d by dt, I get the velocity. Only makes sense, because the velocity is the rate of change of position. So what do you get? Now how do I get the acceleration? That's crazy. So you take the derivative of the velocity, which is a second derivative of the position. And here you get 8. So whatever is traveling according to this function, what's true about its acceleration? It's constantly accelerating. Totally. Oh yeah. Oh yeah. You've seen this kind of problem before, for sure. Because the minute we learn derivatives, you can start doing this kind of problem. In this section, they're going to take this problem and they're going to ask questions A through F about these. So on a position problem, if they start asking you velocity and acceleration, the very first thing you do is just do those. And then make sure you use the correct one. So, for example, real quick. I don't know, most time people don't know this, but anyone know what it's called when you take the derivative of the acceleration? The jerk. I love it. So you'll see a shirt that says "Don't be d cubed dt cubed s of t." Right? Don't be a jerk. So think about what that means. Acceleration is not constant. This is like my first car. It would do this. All right. What'd you say? It's really jerky. That's the jerk. It makes sense. It makes physical sense. I love it. Here, is this jerky? What's this guy? Yeah, so it's not jerky. It's a nice smooth thing. Not my first car. My poor little first car. Okay, so let me ask you some questions about this. Let's start off nice. What is the position? In fact, let me tell you, S is in meters and C is in seconds. Yeah, because a huge part of this, of course, is units. Oh, shit. So what is the position at t equal 2? When is it not moving? And let me do one more. Where is the, let's say it's a particle. When the velocity is, what you got, Jeff? I don't know, Jeff. Let's do, when the velocity is 16 meters per second. Try to do those three problems. Okay. So the very first one, if you have trouble with this one, you should feel really bad. You just should. So what is the position at t equals 2? You just do what? Plug in 2 into the position function. It's crazy. And you get 16 minus 16. So it's at 0. So it's, and where is it at time 0? When t is 0, where is it? 0. I mean, why does that make sense? Because this would be how if you graphed it? Right. It's parabolic motion. So it's like it goes away from me and then comes back. So it's like a boomerang. You threw it correctly, right? Somebody doing it? So this is 0. 0 meters. When is it not moving? What do you do? Set the velocity equal to 0. That's crazy. All right. So if you take the velocity, set it equal to 0, you get t equal 1. Where is the particle when the velocity is 16 meters per second? So what do you do? Yeah. So take the velocity, set it equal to 16. When you solve that, you get 3 seconds. So where is it? You just plug 3 in the position. So I love that kind of question. I'll say, when the acceleration is this, where is it? Or what's the velocity when the acceleration is this? So you have to do like a couple steps. So just plug 3 in. And what do you get? 12. I like this. 12 meters. Coolness. Not crazy hard at all, really. It's actually kind of nice. Let it be nice. Now, let me show you something that's very useful. This one's pretty simple motion, but let me just show you. So at t equal to 0, it's at 0, right? When does this sucker turn around? What would it mean to turn around? What happens if something turns around? It first has to stop. And where does it stop? 1 second, right? At 1 second it stops. So think about that. What would that be of this? That would be the what of this? The vertex of that. I like it. Negative e over 2, blah, blah, blah. Stay with me now. So at 1 second, where is it? At 1 second, where is it? No, that's how fast it's going at 1 second. At 1 second, where is it? Negative 4. I like it. So actually, I need to do this backwards. So at t equal to 1 second, it's at negative 4. Now t equal to 2 seconds, where is it? 0. All right, let me stop for a second. So at t equal to 0, it's at 0. At t equal to 1, it's at negative 4. At t equal to 2, it's at 0 again. So like somebody threw this thing backwards and it came back at me. All right. At t equal to 2, at t equal to, sorry, that's 2. T equal to 3, it's at 12. Whee! So forth. I like it. Now, why would this be useful to draw? If I ask you what's the total distance it's gone after 2 seconds? Before I drew this picture, a lot of you guys would have said, well, it went 0. But that's where it is. How far has it gone? How far has it gone? 8 meters. It went 4 meters back, and then it came back. So it went 8 meters. If you draw a little picture like that, it will help you answer that question. Not where is it after 2? That was this question. How far has it gone after 2? Well, it's gone somewhere. I like it. So if I moved all this shit from one side of the room to the other, I'm like, oh crap, I was supposed to leave it, and then I moved it all back, and somebody came in like, what have you been doing? Oh, shit's in the same place, you didn't do anything. Right, so that wouldn't be fair. So this is just being fair to the poor little dude. It actually went somewhere, just came back. Okay. So let me give you one to try. A little bit more interesting. Let me ask the same kind of questions. Let me ask you some questions here. How about that one? You should go ahead and start doing some derivatives. Let me actually make that one this third. Make sure you guys are on the right track. See when we gotten the velocity figured out?
Yeah, 81 over t squared plus 9 quantity squared.
Missing something though. Yeah, minus 9t squared. Here, so let's take a look at why that is. How do I do this guy's derivative? I'm going to use, so I do top first 9 times the bottom minus the top. The root of the bottom is 2t squared. All over t squared plus 9 squared. So you get 9t squared minus 18t squared, so you get negative 9t squared plus 81. So that's 81 minus 9t squared. All over that business there. So the acceleration is going to be exciting. Yeah, that's the word, Jeff. Really smart about this kind of problem. You're going to be curious about where things are zero, which means you want to factor things, which means you don't want to distribute and combine like terms. That's the opposite of factor. So when you do this second derivative, don't start multiplying shit together. Start thinking factor it. Because then you can see where it equals zero. Catch up to you guys. So top's derivative times the bottom minus top times the derivative of the bottom. How do I take the derivative of the bottom? Try and roll. That's right, because the inside is more than just t. So the 2 would come down. T squared plus 9. And the derivative of the inside is 2t, right? So this would just become 4t when I bring that out here. So the 2 comes down, times this to the first. Derivative of the inside is 2t. 2t times 2 is 4t. I just put 4t. All over. T squared plus 9 to the 4th power now, sir. Bless you. Now, you're allowed to do what I'm about to do because you don't have to write the factorization. How many t squared plus 9s can everybody lose? 1. He can lose 2, but he can only lose 1. So I'm going to lose 1 t squared plus 9 from everybody. It cancels. You can never just do this, because both of these being divided by this, but I took care of both of these, so that's legal. And now it's distributed. You can get your like terms. Yeah. Negative 18t cubed minus, what is that? 162. T plus 36t cubed minus 324t. Now you just get your like terms together. So we get 18t cubed minus 486 t all over this business. That's the acceleration. Second derivatives very often suck, especially if it starts off as a quotient. It's going to be a little loose. But this is stuff you can sink your teeth into. Meaning you just work at it. There's no concept here. It's just pure raw. So, let's start here. What's the velocity at 1 second? So velocity at 1 second, plug a 1, I get 81 minus 9 over 100, right? So you get 0.72 watts. Still the same thing. Meters per second. What would acceleration be in, by the way? What units would acceleration be? Yes, because it's meters per second. Per second. I love it. So people are always, when you look at meter per second squared, you're like, what the hell is a square second? What is that? Right? That's Picasso time. No. Cube is time. I like it. When is the velocity positive? What do I have to do to figure that out? I got to first figure out when the velocity is 0. I like it. Because then around that it might be positive, negative. Right? So I've got, I want 81 minus 9t squared to be how related to 0? Is everybody cool with that? Because like the bottom is going to cancel, it's related to 0, so I can just multiply by it. Is the bottom ever 0? Hell no, because they're not using complex time, thankfully. How about after I seconds? No. I want this to be greater than 0, that's positive. I hear you. Add that over, divide by 9, I get t squared less than 9. So you remember how to do this? So that means the absolute value of t is less than 3. Is that cool? Which means what? T would be officially, mathematically, between -3 and 3. Real quick, why does that make sense? What kind of thing is this? Parabola that opens down with some intercepts, right? In fact, 3 and -3 are the intercepts. When is it positive? In between the intercepts, that's when it's positive. That's all we just did. It's another way to do it. You don't have to do it that way. You can do it visually. It's going to be positive in between its intercepts. Okay. Now, a lot of these problems are going to give you intervals for t. Like t is from 0 to whatever. Like it. So I didn't really do that. So this is officially the answer here. Between -3 seconds and 3 seconds is when the velocity is positive. When is it speeding up? Okay, so what would that mean, speeding up? What about the acceleration? That's the truth. No. What if I'm going backwards, but my acceleration is positive? Am I speeding up? Oh, I love it. All right. When is this speeding up? When is it speeding up? When is the pen speeding up?
On the way down.
On the way down. Acceleration and velocity are the same sign. Then they're going to work together. If my velocity is negative but my acceleration is positive, it's changing my velocity in that direction. So I'm slowing down. And then maybe I'll go forward. So when you see a question that says, when is it speeding up? That means that acceleration and velocity have to be the same sign. So now I know exactly when velocity is positive, which means I also know when velocity is negative. Now I just got to figure out when is acceleration positive and negative. What's the acceleration? Oh yeah. Yummy. Does 18 go into 486? You would hope so. Let me see, does that make sense? Yes, it does. It should, I think.
It goes in, if you divide it, it goes into 27.
All right, here we go. So I want 18. Let's figure out where this is 0 first, and then we'll go from there. So I could kill at 18. So 18, 18, 18. So I get t cubed minus, who is it? 27? Oh, that so kicks ass. I wish I could take credit for that, but that was a problem for the book. Okay. Why does that kick so much ass? You guys? It's a perfect cube, yeah. Now, there are 3 answers to that equation. Does everybody understand that? Because I could factor this, there would be a big dude that would quadratic formula, but those 2 answers would be complex. We're not dealing with complex time. What the hell would complex time be? I don't know. All right. When's our office going to open? In 3 hours? So what's t? T is?
3. Or plus or
3.
minus 3.
Well, it's 3. Yes.
How about the T for 46?
Oh man, I got so excited about this being a cube. There's a t right there. We're going to get gross stuff. Too bad for us. So what happens here? It's not quite as pretty. What really sucks about this is I get 3 real answers, and 2 of them are not the prettiest things. Well, what are they? What are the 3 answers? T is 0, and T is plus or minus square root of 27, which is, simplify it. We just write square root of 27 there. So the acceleration is 0 when t is 0 and t is plus or minus rad 27, which is plus or minus 3 rad 3. Because 27 is 9 times 3, and I could do the square root of 9. I like it. Okay, so that's when it equals 0, right? What I really need to figure out is, for example, when is it positive and when is it negative, right? So what I can do, I don't know if you guys have done this before. Actually, I know you guys have done this before. Here's where it's 0. You guys remember making like a sign diagram? You should have done that in pre-calc. So what am I going to do? I want to know when a function is positive or negative. Well, I know when it's 0. So the only way a continuous function can go from positive to negative or vice versa is if it goes through a door in the x-axis, which is the x-intercepts, which are what those are. In this case, t-intercepts. So these are doors. So all I got to do is, what's a number in here that's really nice? What? I like that. Got Yoda over there. So if I plug a 1 in to this equation, is it positive or negative? You can see very quickly that it's 18 minus 486. It's negative. Let me push it. Let me see if you guys remember this. If I say this, if I say multiplicity, who knows what the hell I'm talking about? Multiplicity. Yes, I love it. Multiplicity actually relates to how often a root shows up. So if I had a piece of something that was t plus 1 squared, that would be a root of negative 1. It would have multiplicity 2. I love you guys so much. All right, again, if you had a really good pre-calc teacher, they would have taught you this because it's useful shit. It makes it very quick to do this kind of thing. We're going to be doing this kind of thing a lot in chapter 4, which is in our very near future, right? Sign diagrams are going to be every damn where. Ugh. So you want to know how to do them quickly. I don't want to plug a number in for every flipping, screw that shit. The multiplicity of each of these roots is 1. They each show up once. It didn't come from something squared or something. Yeah, this is squared, but I can factor it. Right? So these are each a multiplicity of 1, which means, I love you guys so much. It has to change signs. So what's a parabola? If the multiplicity 2, that would mean it's parabolic, which would mean it turns at its root. Which would mean if it's positive here, it's still positive on the other side. This has got an odd multiplicity, so it goes through. Why is that so kick-ass? Because now I know around every door it's going to change sign. It goes through the door, it goes through the door, it goes through the door. It doesn't come to the door and go, nah, screw that. It goes through the flipping door. You're all with me like, what the fuck are you saying? But hopefully some of you guys, I hope to God. Is this familiar? It looks like this is familiar to a few of you guys. It's so stupid useful. Teachers that think ahead will teach you stuff that will help you in the next, and it is pre-calc, you would hope. People would get you ready for this. So when is acceleration positive?
At -3.
From -3 root 3
to 0.
to 0.
Unity. 3 to the square root of 3. Infinity.
Yep. So of course it's negative at the other places. All right. So let's see if we can do this. Let me put what we know about velocity and acceleration together so this answer is easier to see. Take all this stuff away. This is all stuff. Go away, go away. What do we know about the velocity? It is positive in here and negative out here. Cool. That's what we know about the velocity. So that's the velocity. What about the acceleration? Let's put it on the same scale. So where would -3 rad 3 be? Is it going to be bigger or smaller negative than -3? It's -3 times rad 3, so it's going to be further out. And same thing with 3 rad 3. And 0's in there. So we just figured out that it's right there. So it's negative, positive, negative, positive. All right, so when are they the same sign? When are acceleration and velocity, when are they the same sign? So when is it speeding up? From -3 to 0, I love it. They're both positive. So there's both positive from -3 to 0. That looks like a plus or minus here. When else are they both positive? Any other time they're both positive?
Oh, no, positive is good. No.
Yeah. That's the only time they're both positive, isn't it? Right? Is that cool? All right, now when are they both negative? Negative infinity. -3 rad 3. Any other time they're both negative? Yeah, from 3 to 3 rad 3. So those are the time intervals where what's happening? Where it is speeding up. Not where it's accelerating. This thing is always accelerating, except where acceleration is 0. But it's where it's speeding up. So when you hear the word accelerate, you normally think that that means you're speeding up. That's not true. If you're going backwards and you're accelerating, it means you're slowing down. Right? This pen is constantly accelerating, right? At the same acceleration because of gravity. But when it's going up, it's working against acceleration. That's why I want the signs to be the same so they're working together. Then this thing is speeding up. I like it. Okay. That was a disgusting problem, an example of this. But do you see how drawing these diagrams out, drawing a diagram like this, drawing the diagram like I showed you with the curvy stuff, that is so helpful. It makes it more physical and more visual. And a lot of us have a big visual component to how we look at things. Makes sense. Okay. That was some of the freakier questions I'll ask you in that section. Let me see. Oh, I got plenty of time. This is awesome. Let me see if I can push this a little bit. Okay. Let me show you something that's really, really kind of cool if you haven't noticed. What's the area of a circle? Pi r squared. All right. I'm not going to show you. There's a beautiful proof about why that's true. You take the circle and you make it into a rectangle. So you want to see that? Yeah. Sort of? Okay. All right, you ready? This is really cool. I mean, you should never just accept a formula. You should say, where does that come from? Show me. You really should. And if the teacher can't answer you, they're not doing their job. I love this shit. This is awesome. If I take a circle, cut it in half, and then I cut out to the edge, but not through the edge. Do you understand what I mean? So cut it in half. It's cut in half, right? Now it looks like it's Canadian, right? See if anybody watches. No, nobody watches that anymore. Okay. Yes. So just take the top half. We're going to do it the bottom half in a minute, but cut these little triangles out. And in reality, this works. This truly works when you make an infinite number of triangles, but let's not do that. That'll take time. So then I could pick it up and do this. Is everybody cool with that? I could open it up and lay it down. All right? Real quick, how far is this? Say again? How far is it? Not how many degrees. How far is it? Or how many radians? Not how many radians, but how far is it? How long is that? Pi r. I like it. Because the circumference, of course, is 2 pi r. Let me stop. Is everybody with me? So if I open this sucker up and I lay it down, it's going to look roughly like this. Is that cool? Good Lord. Talk about rough. Oh. That's rough.
But with like a curved top, right?
No. You can flatten the top out, of course. You can take a straight string, and then loop it around the base of a trash can or something. So I can undo that. That's all I'm doing. Picking this up, flattening that out. So how long is this?
Pi r.
Pi r. Now, do the same thing to the other side. Remember, there's actually infinite triangles. Somebody had a lot of time. And a very precise pair of scissors. Atomic width scissors. If I take that and I fit it in, open it and fit it, what shape have I just made? And of course it becomes that shape more and more when you get more infinite triangles. How long is this? R. So have I not just taken the circle and made it into a rectangle? People will argue not a perfect rectangle, but remember what I said. Let the number of triangles go to infinity. The limit as the number of triangles goes to infinity, right? Then it becomes approaching a perfect rectangle. Now what is the area of this rectangle? Pi r flipping squared. Shit, yes. All right. So how do I... Have you guys, anybody ever seen that before?
No.
Anybody ever seen it before? You've seen it before? Okay, I don't feel so bad. I don't see why. How can you say this and not show that? It's a beautiful thing about rearranging a shape into a shape you know something about. Just like we take a function, we rearrange it into functions we know something about so we can figure out what its derivative is. Build on what we know. Now, that wasn't my intent, but I needed to show you that if you never saw it. All right, let me take that over. Now, what is DADR? Yeah, so what am I taking the derivative with respect to? R, so R is my input here, that makes sense. So it's pi r and the 2. What is that? What is that? Circumference. That's a circumference. What the shit? And if you think about it, what does this mean? What happens to the area of a circle if the radius gets dr bigger? Dr is like infinitesimally small change. So what I love to think about is, how does the area of the circle change if I put one thing of tape around it? One thing of tape on it. How much will that area change? It will change by the circumference. Because that's what I just traced out the circumference, right? If I keep adding more and more tape, it's going to keep changing by the new circumference. That's what the area is going to change by. So it makes sense that the derivative of the area is the circumference. You see this kind of thing with a lot of geometrical items. That's almost too nice to believe. Okay. So one reason I wanted to do this is because it gets us starting to think about paying attention to this. Really, really, really paying attention to this, right? So let's do this. What if I had, if you throw a rock into a pond, and this is a classic example of this. Some of you guys might know where I'm going. If you throw a rock into a pond, what shape does the ripple coming out from it take on? This is a nice glass surface pond, there's zero wind, no fish in this pond. Everything's dead in this pond. And you're like, screw you, pond. Throw a rock in there. Pond. If you could just try to pick the pond apart. So these circles ripple out from where you threw the rock in, right? You with me? What's happening to the circles is get away from the point where you threw the rock in. They get larger. Anybody work with sound at all? Anybody work with sound at all? Anybody? No? Look, no. So if you do, you know that like when sound emanates from some source, it has to cover a larger and larger surface area. Sort of like you think of it as a sphere going out. That's why sound decreases as you go further away from it. That's one reason, is because that energy has to get cover this larger area. And the same thing with light happens. It's called the inverse square law. We'll hit that later. Here, it's not really that. I've got this pond, I throw a rock in, and I have these ripples emanating out that are all circular, right? How are we doing so far? So what I'm curious about is, how quickly is the area of a circle changing at a certain time? Right? So this will be dA d what? How quickly is the area of one of these circles changing at a certain time? dA d t. Okay. So what is it going to depend on? Well, area is pi r squared. What do I take the derivative of with both sides with respect to get what I'm curious in? Obviously with respect to t. So what happens if I do that? I'll do this side. Thanks, Jeff. No second derivative. But what is the radius staying the same for the circle? Isn't the radius also changing with respect to time? Isn't this an application of implicit differentiation, but a lot better? A lot better. Don't freak out. Why is this better than before? Because I'm taking the derivative with respect to time, and time does not show up in the equation. So if I do this side, what's the derivative with respect to time? It would be 2 pi r times dr dt. That is the chain rule piece. Because what's inside of the square? A function of time. So when you take a derivative with respect to it, when you take a derivative of it, you better multiply by the derivative of the inside. So this is implicit, but with a third outside variable, something that controls the other variables. So this is the most often used one, is time, because time is the controller of everything, right? I get older, you get older, that gets bigger, that gets smaller. So everything's kind of dependent on time. So in order to figure this out, what must they tell me then? A couple things. And to figure this out, I need to know the radius and how quickly the radius is changing, right? Okay, so let's say I want to know dA dt at a time when the area is 4 pi. So how quickly is the area changing at a time when the area of the circle is currently 4 pi? And we know, I'll tell you this, dr dt, how quickly is the radius changing is, we'll say it's 2. Let me give us some units here. Feet per second. Pretty quick ripple, but we'll go. So they have to tell you some information. When you take the derivative of a function with respect to some outside variable, you're going to get a couple of rates. They have to give you one of those. Also, notice how an r is still left alive. So they have to either tell you what the radius is or give you a way to figure it out. Now, what's the radius at this time? 2, right? Pi r squared. That's 4, so r must be 2. So dA dt equals 2 pi times 2 times 2, because that's what dr dt is. A lot of 2's. So what's dA dt? 8 pi. 8 pi what? Feet per second. So it's really interesting. You see why the name of this section is related rates. There are 2 rates. They are related because they are in an equation. They are related to each other. dA dt depends on dr dt. They're related. So I start with just a known equation. And then I take derivatives of both sides, and now I have a relationship between the rates of change. Now, if you remember what I said earlier, differential equations takes that process backwards. If I start knowing this, I want to work back to this, which is not always very easy. Let's do another problem. Actually, let me see. No, I won't do that here. Yeah, let's do this. Perfect. Air pumped into spherical balloon.